Hello, I'm Amy Glazier. I work at UNC Chapel Hill, and what I work on, the science that I do, is I work on exoplanets. I work on finding planets outside our solar system, and it's a really exciting time to be doing that. Just since I've been around, just since I've been alive, we've gone from knowing about like 0 exoplanets to now we know about 4,000, quite more than that. We're approaching 5,000. And that's really awesome. You might think, oh, that's an awful lot. That's enough to last your entire PhD, isn't it? But there's kind of a catch in that, so yeah, we know about all of these exoplanets, but the vast majority of the exoplanets that we know about orbit single stars like we do, because that's where we focus our searches, because we want to find planets that are like Earth. The thing is, though, stars tend not to be just single stars out there. Most stars are in binary, so two stars, or in multiple star systems. So there's this kind of disconnect between where we've been looking for planets and the configurations that stars tend to be in. And consequently, less than 10% of known exoplanets are in binary systems. For a long time, astronomers even weren't sure that you could have planets in binary systems, whether they could form with the influence of those two stars messing around. So what I want to know is how many more planets are out there in binary systems, and what can they teach us? Not just about the planets themselves, but kind of in general, how could planets still form and potentially be habitable in binary systems? So the type of binary systems that I'm looking at specifically are eclipsing binaries, where the two stars in the system eclipse each other over time. And so what that looks like, if you're looking at how the brightness of the system changes over time, as one star eclipses the other, you can see that the brightness will dim as one star blocks some light from the other, and it'll dim again as the other star blocks light from the first star. And so stars that are orbiting each other, because of the laws of physics, there's no reason for their orbit to change at all. They're going to sit there and just keep orbiting with a very well-defined period. The question is, though, what if they don't orbit with a well-defined period? What if the eclipses of these stars don't happen at the times when you would predict them to based on the period of the star? And that gives me a key to looking for planets in binary systems, because if you've got a planet in an eclipsing binary system, that can change the timing of the eclipse. It can vary the timing of the eclipse. And there's two ways that it can do this, either by, if the planet is massive enough, by actually tugging on the stars and changing their orbit just slightly so that eclipses don't happen at the same time interval all the time. Or the planets can even just change the time that it takes for light to travel from the system to you, just because because of the influence of the planet's gravity, light has to bend around it. So it's going to take a little bit longer if it has to go around that planet first to get to you. So what this means is we can use eclipse timing variations in the eclipse timing caused by these planets to actually find the presence of planets in binary star systems. So that's what I've been working on for my work with the space grant. The telescopes I've been using to do this, it's called the Every Scope. There's two of them. One of them lives in the southern hemisphere, the other lives in the northern hemisphere. And they've been out, the first one has been operating since 2015. The second one, I got to help build it. It's been around since I've been a grad student. And that one we deployed in 2018. So these are the telescopes that I use for my work. Let me tell you a little more about them so you can understand how they work. They look like mushrooms, and that's for a reason. So my research group at UNC Chapel Hill designed and built these telescopes. Each of those black circles that you see on the mushroomy structure, each of those black circles is a camera. And so there's about 24 on each of the Every Scopes, and those cameras take images every 2 minutes. So if I say want to know really precisely the timing of when an eclipse happens, it helps be able to take images every couple of minutes instead of having to wait, say, half an hour or 2 days or something. And the really cool thing about these telescopes is that they observe the entire visible sky. That's why the cameras are positioned all over the dome so that we can observe the whole sky all at once. Because normally, if you were trying to look for, if you're trying to look for eclipse timing variations, if you're trying to look for planets around binary stars, you'd have to just stare at one star for a long time, long enough that you can see if the eclipses are changing in the time interval that goes between them. And that's not very efficient if you're trying to find planets. But with the Every Scope, instead of looking at one star, I get to look at all the stars all the time, all at once. And so that makes it a lot easier. Instead of having to focus on one star, I can look for all the binary stars in the every scope field of view and look for eclipse timing variations with all of them. And that hasn't really been possible, at least not easily with previous instruments and telescopes up to now. So it's really special, and I feel lucky that I get to do this. So when I say I'm looking for eclipse timing variations to look for planets in binary systems, let me show you what that actually looks like. So when I say eclipse timing variation, what I mean is I'm looking at the difference between the observed time that you actually see an eclipse take place versus the calculated time or the predicted time that you would think that the eclipse would take place based on the period of the binary system. And to visualize this, we plot it so that on the vertical axis here, the y-axis, you've got that difference in observed versus calculated time. And then on the x-axis, you've got just the time, so you can see how that how the difference in observed versus calculated time changes over time. And so if nothing's happening in a system, if you don't have any planet, the stars aren't really moving, they're just kind of chilling, being stars, then your eclipse timing variation, that difference in observed and calculated times, it's always around 0. So that's not very exciting, but it's good to know because that tells you that there's probably nothing going on with that system. Now, where it gets interesting is if you do see variation over time in how the eclipse timing changes. So if, say, the eclipses are happening longer and longer apart over time, then that tells you that, oh, these stars must be moving farther apart. And the converse is true. If the eclipses are happening sooner and sooner, closer and closer together, that means the stars are spiraling inward, and they might even collide after some time. And so neither of those are planets. This is where the last case comes in. What if you've got, instead of always increasing or always decreasing, what if you have that difference in observed versus calculated time? What if that changes periodically? Sometimes it's sooner, sometimes it's later. It just happens in this kind of nice sine wave periodicity. That's what you're looking for if you're trying to find evidence of another planet, of a third body orbiting these two stars. So that's what I've been looking for in my work. Now, I've got a sampler of findings for y'all. I picked out two of my best looking plots. And the good news is all the work that I've been doing developing the pipeline, the algorithm for looking for eclipse timing variations, it works. It works great. The only trouble is there's a lot of stars, and so it takes a long time to actually find planets. So far, I'm still in the searching for planet candidates phase. But what I have found is that for the targets I've looked at so far, I have pretty much gone, okay, there's not really any variation away from 0 for either of these targets I've got here, for example. So there's probably nothing going on, no planet candidates in these systems. And so now what's left for me to do is to keep going, keep looking. And that's why I'm really thankful for this space grant. It's with projects like this, there's always a risk of like, you don't know how quickly you're going to find stuff. And so I really am thankful for having the ability to take on this project and the freedom to work on it. And I can't wait to see where it takes me. So stay tuned. There's going to be more to come.